right, so we're going to go ahead and start section 8.3 here. We've been talking about confidence intervals, and we're going to shift to talking about confidence intervals for estimating a population mean instead of a population proportion. And one of the things that you want to keep in mind, because in statistics, these are really the two main things that we are trying to estimate about a population, is either what a known proportion is for a particular variable or what a known average is for a particular variable. And the key distinction between these two things is that when we talk about proportions, typically the variable that we're measuring is categorical in nature. For example, if you were to ask people, do you prefer vanilla ice cream or not, their answer is not going to be a number. Okay, their answer is going to be yes or no. And so in that case, we're measuring a categorical variable, okay, something that's more not quantitative in nature, okay, and so that is distinguishing that it's a proportion as opposed to calculating an average. That would be a response that people would give that would be quantitative in nature, like what's the average number of times that a student would get gasoline in a month. You ask them that question, they're going to give you a number of how many times they fill up their gas tank. Okay, so we've already kind of discussed briefly this formula here, which is what we see on the formula sheet for confidence interval. It's a very generic formula. We know that technically the statistic that comes out in front, that is either going to be your sample proportion, okay, or now we're going to shift gears here in this section, and that is going to be your sample mean. Okay, and we're going to create this window of intervals like we've been discussing in this chapter. Okay, so that's why we see the plus or minus after it. Okay, when we dealt with proportions, after the plus or minus, the critical value was a z-score, and that was associated with the normal curve and what our confidence level was, and we essentially used 0 for our mean and 1 for our standard deviation, and then whatever our confidence level was, we split that in 2 to allocate for the two tails, and that would give us our z-score. Okay. Now, I will draw your attention right now to the fact that you do see a z-score here also in the setup for a confidence interval for means. That is going to change, and we're going to discuss that here today. But right now, I'm going to leave that as a z-score, and then the other piece is what we call the standard deviation of your statistic. Okay, so with proportions, this formula right here is on the formula sheet, and it's labeled as, I think, maybe the standard error of proportions. If you were to look on the formula sheet, you would see that this formula down here is the formula for the standard error of a mean. And so even though this is the formula they're giving you, we can kind of put these pieces together to create our confidence interval formula. Okay, here are our conditions that we need to check anytime we construct a confidence interval for means. And the one thing you'll notice is the first two conditions are basically the same, whether you're creating confidence intervals for proportions or for means. And that is, we want to make sure that our sample is random. In order to check off the independence condition, we need to do the 10% condition. But here's where you're going to see something different. Okay, when you're checking for normality, this is different for means than it is for proportions, okay? There actually are going to be 3 different ways that you could check off normality for means. Right now, we're just going to discuss 2 of them because these are the 2 we've already mentioned. One is if the problem flat out comes out and just tells you that your population is normal, that is enough for you to then conclude that the shape of your sampling distribution would also be normal. Okay, so we could just say, oh, well, ours is approximately normal because the population is normal. The second thing that you could use to check off normality is what we call the central limit theorem. And this is, as long as the sample size is 30 or greater, then we can assume that the sampling distribution is approximately normal. Okay, and there will be a third one here that'll come up later, but right now those are one of those two things we could check off to kind of say that the sampling distribution is normal. Okay, so let's go back and revisit kind of this idea here of here is our formula for confidence intervals for means. And it says suppose we wanted to construct a confidence interval. We're trying to estimate what we think that mu would be, the population mean. Okay, and we notice here that when you kind of put these pieces together in this formula, you see right here, remember what this variable right here is representing. That is representing what your population standard deviation is. Now, here's what's unrealistic about this. If we know all the values for the entire population, which is what we're assuming if we are given the population standard deviation, then why wouldn't we just use all of those values from the entire population like a census in order to not try to estimate what mu is, but to factually calculate the exact value of mu? Then we don't need a confidence interval to try to estimate it, okay? So, it's a little unrealistic that we would have access to the population standard deviation and then not just go ahead and calculate what the population mean is. Okay. Now, I'm going to illustrate this for you here, and you're going to see what we're going to do to kind of help account for this here. Okay. But this is talking about a high school football team, and they want to estimate the weight of high school offensive linemen in the state of Texas. Okay. So it says we take a sample of 50 high school offensive linemen, so that's our sample size. It says we find that their average weight is 220 pounds. So that's our X bar, 220 pounds. Suppose that it's known that the population standard deviation is 26 pounds. And this is kind of the unrealistic part to that. Because if we know the population standard deviation, then we shouldn't have to just take a sample of 50 high school football players from this school. We should have access to all of those values here. But it says assume that the conditions are met. They're asking us to construct but not interpret a 95% confidence interval for mean. Okay, so we would use this formula right up here that you're seeing up above here. We would take our sample mean of 220 pounds, plus or minus, we're going to fill in our z-score there in just a second. Okay, and then the standard deviation for the sampling distribution of X bar would be the population standard deviation of 26 divided by the square root of the sample size. Okay, probably have memorized what the z-score is for a 95% confidence interval, but this is how we calculate it. Okay, and it comes out to 1.96. That's what we fill in here, and we end up getting that our 95% confidence interval is we're 95% confident that the true average weight of these offensive linemen here for the state of Texas is somewhere between 212.79 pounds and 227.21 pounds. Okay, but you'll notice underneath here it says, however, in practice, we rarely know the population standard deviation, and instead what we end up using is we end up having to use the sample standard deviation in place. Like we would end up not using sigma, but instead right here where sigma is, we end up using the sample standard deviation. Okay, and there is a major issue when we do this with exchanging that piece of the formula. Okay, and it really happens particularly when your sample size is small. Okay, so that's where we're going to have to make a change here to our z-score. Okay, we're going to be using something called a t-score instead. Okay, and the reason that we end up doing this is it makes the capture rate more accurate. Like 95% of the time, if it's a 95% confidence interval, it would end up capturing the mean. Okay, so let me just illustrate for you a little bit what a t-distribution is. Okay, if you think back to z-scores, right here's the formula for z-scores. In fact, well, I guess, sorry, it was really this formula right here, okay, where we would take our statistic minus our parameter and we would divide it by the standard deviation, okay? That would look something like this right here, okay? Okay, the issue is when we swap out the population standard deviation for the sample standard deviation, now this is no longer a z-score. In fact, it's actually going to be what we call a t-score. It does not have a normal distribution, okay? So what we're going to do is, I will tell you what is the same is the t-score has a single peak at 0, just like the z-scores do, but there's a lot more area in the tails. Can you notice this here, how there's more area stretched out over here on the left and on the right, as opposed to a normal distribution that's made up of z-scores. Okay, so I want to talk a little bit about the phrase degrees of freedom here with you, and then we'll put this all together so that you'll see how the t-score is used instead of a z-score, and this is only with sample means, not sample proportions. Okay, degrees of freedom is sometimes a complicated concept for some students. I'm going to just try to explain it to you in this way. Let's forget about statistics here just briefly, and let's just pretend that you are in love with hats. You have a variety of hats at home. In fact, let's pretend that you have 7 hats and you want to wear a different hat every single day of the week. Okay, so the very first day of the week, you could pick any one of the 7 hats, but once you wear one, then it's eliminated. And then for the second day, you would have 6 hats to choose from, okay? So let's say the first day you pick this lobster hat. The second day you go with this yellow hat. And you can see all the way down until you get down to the very last day. Okay, when you're down to the last day, you no longer have the freedom to choose which hat you're going to wear if you're going to wear a different hat every day. Okay, you had 7 hats to begin with, but you technically had 6 days of, we'll call it hat freedom, where you could choose a different hat, like the hat you wore could vary. Okay, and so when we talk about degrees of freedom, the formula is actually quite simple. It is the number in your sample, the n, minus 1. Okay, so let me give it to you an example here with numbers. Let's say that you a claim was made that the average is going to be 5 in a sample of 10 values, okay? And the first 9 values are completely free to vary, to be whatever they wanted. You know, I could go around the room and say, give me any number, and different people, first 9 people could give me any number they wanted. We'll just pretend these are the first 9 numbers. However, if we want the average of these 10 numbers to be 5, once we get down to the 10th number, we are no longer free to allow that number to vary and be whatever it can be. It is locked in. In this case, using these examples that I gave here, this 10th number would have to be the number 4 in order to add all of them up, divide by 10, and get the average to come out to be 5. And so what did we have? We had 9 degrees of freedom, which was really 1 less than the number that was in our sample, because the first 9 numbers were free to vary to be anything they wanted. That very last one is kind of locked in. Okay, so degrees of freedom is always the formula n minus 1. And so when we talk about degrees of freedom with the t-distribution, it's the same. The formula is n minus 1. Okay, a couple of things I just want to point out with this is the t-distribution. Again, it's a bit greater than the standard normal curve. It has more area in the tails. as your sample size increases, think about what that would do to your degrees of freedom, okay? As the sample size increases, then that means that the degrees of freedom would also increase, okay? So here's basically our two options. If we know the population standard deviation, then we would be fine with using a z-score, which means we would use inverse norm to get that critical value there. Okay. However, if we don't know our population standard deviation and we're forced to plug in our sample standard deviation there, that is when we have to shift to using a t-score value. Okay, so in the next video, I will show you what that is going to look like.